Welcome to the next video in the systems programming video series. We have just finished up part one of the assignment for, I think this is week 3 or assignment 3, week 4, I guess. And we're moving on to part 2, which is working on sorted snacks. So implement a program sorted snack bar.c that allows the user to add snacks to the snack bar and display them in alphabetical order. Your program should have the same features as last week's snack bar, but should use a linked list to store the snacks rather than an array. So here's how to compile, and then to run, it will prompt for a number of snacks, and then after prompting for a number of snacks, we'll prompt that many times for 3 pieces of information for the snack. After prompting all of the prompts, it will then return all the information right back, this time in sorted order, sorted by the name of the snack. So we will implement this function insert sorted. This will create a new struct and return the first item in the list. And then we implement a function clear that will clear the list. Okay. Getting over here to sorted snack bar. You can see where I've already made a first implementation, so these includes are okay. This struct snacked was already distributed with the code, so I did not design this. It's got the fields of a, snack basically, and then what makes this a linked list is that every snack has a pointer to the next snack in the list. We will implement a function insert sorted. The header for this function I did not design, that was distributed with the code. So it will return a pointer to a snack, and it takes in a pointer to a snack, and also takes a bunch of information for the new snack to be constructed. It also has to insert it in sorted order. So we'll get into that in a bit. But you can look at the code here if you want to just skip straight to the first solution that I made. Here is the function clear, which deletes everything in the linked list, essentially frees it up. And here is main, where we prompt the user for info and do it in a loop for however many snacks they want, and then print the output. But okay, so now I'm going to comment all of that out. And we'll implement it from scratch. Oh, that does not get commented. Okay. Possibly the first thing to talk about is the way that we're going to deal with a linked list of size 0 or length 0, right? Which basically means there are no snacks. Now, coming from I have a bit of experience with Java, and so a lot of times if you were going to work with that, you might have basically just an instance of a class with no initialized data, and that could be like something like that, right? There are various ways that you could design this. And so you could say, like, you could have some signal in the initial instance, like the first node of the linked list, telling you that it's empty, for instance. There are other ways to design it, but in C, essentially, you can't check to see whether a particular instance of a struct is empty or not. And therefore, what we probably ought to do is say that the pointer is null, right? The pointer itself, not even like what it points to or whatever, but the pointer is null if and only if the linked list is empty, which is to say it has length 0. So that's going to be what we treat as the signal for whether the linked list is has length 1 or length 0. So what that means is that by design, by intention, the first thing that will get passed into this will be when snacks is null. And when that is true, we are constructing a new node. So we want to construct this new node and then simply make it make the pointer to it equal to snacks, basically. Okay, well, one way or another, whether we put it here, right, whether the linked list is empty or long or whatever, we probably want to just construct it and then put it wherever it's supposed to go. So let's start this whole thing with actually just constructing the new snack in the list. So let's say snack struct snack star new equals, now I'm going to malloc size of struct snack. I'm going to go ahead and give it its name, quantity, and cost. This is a pointer, so I could deref the pointer and then call its name field. But why do that when you could just use the arrow notation, right? So I'm going to use the arrow notation. New name, that's the name of the new snack struct that I am constructing. I want to copy into it the input name here. So let's do that now. And for that, we'll use stir copy. That is safe in this particular case. Well, I guess it would be safe if I checked that the length of name is small enough to fit inside of new name. New name permits 31 characters because it has 32 space for 32, and the last one has to be the null character. I'm just going to be lazy and not bother with that. Certainly in serious industrial applications, you would want to take all of those kinds of concerns quite seriously, but I mostly just want to get through the assignments because the more interesting thing right now for us is the ideas. So anyway, so I'd like to copy into that destination the passed in name. Okay, great. I now want to set new name equal, sorry, not name, I guess quantity equal to quantity. I'd like new cost to equal cost. Finally, there's new next, which so far as we know, does not exist, and we will again use the null pointer to signal nothing there. We'll redirect this if we decide that we need to change this, but for now I'm setting it to null. We want to check the passed in pointer to see if it's null. So if not snacks, right? So if the pointer is null, right, is effectively what that's saying, then what I want to do is simply return new, because that will, in fact, be the entire linked list in this particular case. That's it, right? So very simple, nice that it fits in a single line and has a simple logic. Okay, from here on out, we know that snacks is not null, and therefore it has a next field. Now let's think about the sort of, there are multiple ways to implement this, but let's think about the way that we would want to implement insertion into the right place for a linked list. And there's some subtle considerations that if you're not used to thinking about pointers, you'll need to be careful about this. Okay, so this is a quick rough diagram of what we might imagine is going on when a linked list stores the very simple data 1, 2, 5, right? So this stuff here is what I am imagining a currently existing passed in linked list looks like when, at some point in the run of a program, okay? But the task is to take a new value 3 and insert it into the correct place. Now, first of all, let's just kind of do a walkthrough of just algorithmically how this would run, you would imagine. We start from the head of the linked list because that's like what we have access to begin with, right? You can't just jump around. You have to have be basically tracking the pointer to the head so that we can get to here. But you start here and you have to compare 1 against 3. And you say, okay, is 3 smaller than 1? Because if it is, then I want to perform the insertion. But it's not, so you move on. And you say, is 3 smaller than 2? It is not, so you want to go ahead. Is 3 smaller than 5? Yes, it is. So you now know that you want 3 to go in between 2 and 5, basically. Now, that sounds nice. You would imagine what you want to do is you basically want to redirect this pointer to now just point to 3, and you'd like to direct 3 to point to 5, and you're done. This now makes a linked list that links everything together in sorted order. There is a problem, though, of doing it, or at least thinking about it this way, which is that there's a crucial step where we said, okay, I see that 3 is less than 5. I would like to go back to 2. But unfortunately, if what you have in your hand, so to speak, is this node and this node, because that's what you're working with at a given moment, and you're comparing these against each other, and you decide that 3 is less than 5, and so this is where you want to perform the insertion, you cannot go back to 2. All of your arrow pointers that allow you to move from one node to the next in the linked list, none of these arrow pointers point backwards. They all point forwards. So if what you have is 3 and 5, and you want to get back to 2, you simply cannot do it. Or you could maybe try to like retraverse the list, but that is so obnoxious and time consuming. Like, just if you don't have to do it, you wouldn't want to do that. So how do we design this in such a way that we accomplish the basic result without losing track of where, right, the 2 that was right before, which we would like to, manipulate its pointers to accomplish this behavior? How do we do it? Okay. What if instead of checking the current node to see whether 3 is less than the current node, we instead use the current node to look ahead to the next node and use that to compare against 3. So here's a little walkthrough of how that would go. We say, now, just at the beginning, you always have to check is 3 less than the current node, because that has to happen at some point. So we just, at the first node, same story. Is 3 less than 1? No, it is not. Okay, great. Now, having done that initial check, let's now start the sort of strategy of saying, okay, use 1 to, now this is a little bit of an abuse of notation, but I think you'll understand what I mean by this. Say like 1.next, for instance, right? If you imagine that 1 is the symbol for the node itself rather than the data, but right, I don't want to like be too tedious here. So let's say 1.next is this next node, and we check is 3 less than 1.next. We're still holding on to the node 1, but we use its next pointer to check if 3 is less than next. That gives, right, if I decided that 3 is supposed to go here, then that gives me still access to all the things I would need in order to perform the manipulations I want. Now, we do decide that 1.next is the value 2, 3 is not less than 2, so the answer is no, and we progress. But then the next thing that we do, once we get over to 2, right, like we reassign the current node to be the node 2, and now we have access to that, and we use 2.next to check if 3 is less than 2.next. 2.next is 5, and so we decide, yes, this is where we are, right? 2.next is, 3 is less than 2.next. So this is where I want to perform my insertion. But because I'm now holding 2, because of the way that I'm setting this up, where I'm using the current node's next pointer to do the comparison, then I still have access currently to 2, and I decide this is where I want to do. So because I have access to 2, I can redirect, you would want to like temporarily save the node 5 so that you can use it later. And then after that, redirect 2 to 3, then redirect 3 to the temporarily saved next thing that you copied over from 2.next. Anyway, and you accomplish this redirection. Okay, great. That is the sort of like strategy that we are about to try to implement. Now, before doing that, let's think of other cases, right? This is like a typical case where the value goes into the middle of the linked list. Let's think about how the value could go to the front of the linked list. That would be like if we were trying to insert the value 0 into this list. And then, okay, that first check that we were talking about, you would say is 0 less than 1. Yes, it is. So put it here. And what that would really mean in practice, what we'll do in a minute, is you take the node, all you do is you set its next pointer to the head of the old list, which you have access to. So that's a fairly straightforward thing. Okay. Now, what about inserting into the end of the list? Like, what if we were trying to insert 6? So you'd say, is 6 less than 1? No, it is not. Is 6 less than 1.next, where 1.next is 2? 6 is not less than 2, so no. So we progress. Is, now with 2 as the current pointer, we check is 6 less than 2.next. 2.next is 5. So 6 is not less than 5, so the answer is again no, so we move on. Now here, we try to access 5.next and ask is 6 less than 5.next, But 5.next is none, right? I mean, the picture that you see here is after we have performed the insertion, but let's actually look at how it is before the insertion is successfully finished. It looks like this, or maybe even it looks like this, where 5 has a null pointer, right? So then you would try to access 5.next, but 5.next is the null pointer. You got to be careful about that, is basically what I'm getting at. But one way or another, you take your 5.next and you simply reassign its next pointer to be this node with the value 6, and now you're done. Okay, so this, I hope, is a relatively good picture telling you how I'm about to implement the insertion. To get started, I want to know whether the current, right, the snacks.name. So let's say if snacks name, and I want to compare that. So let's say stir compare. And I want to talk about names being earlier. So I'm going to put names in the left coordinate. And because I like to do it, you don't have to do it this way, but I like seeing, like, when I write something with a stir compare, I like to put the thing that I'm thinking is earlier in the comparison to the left of the thing later in the comparison. But then what stir compare returns when they are in that order is a negative number. So I need to say if that is negative, which is to say, right, so what I am checking, right, we will enter this if condition if name comes earlier than snacks name. So under that condition, then what do I want to do? In fact, we just discussed that all you do, this is another nice one-line thing to do. No, maybe it's not one line. So what I need to do is set the new next pointer to snacks, the head of the old list, and then return new so that I make sure that I return the head of the new list, which now is new. But now, for every other consideration, I would like to look at snacks next pointer. So you would imagine, well, I'm going to do a while loop because I'd like this to progressively march down the list until I find the correct location. By the way, since we are going to march down the length of the list, I probably want to have some way of remembering what was the head. So let me go ahead and just declare a struct snack head. And that is set to snacks right now, but then this frees me up to reassign snacks so that I can progress through the list. So while now, basically what I'm thinking of is like I want to keep going to the next and going to the next so long as snacks.next is earlier than, or sorry, snacks.next.name basically is earlier than the passed in name. But for that to work, we need to know that snacks next exists. So what I want to say is snacks next and, right? So this is the check, right? This will be some non-zero value so long as snacks next is actually pointing to something, right? If snacks next is null, then this will evaluate to 0 and I'll break out of the while loop. Okay, so continuing. So long as that exists, then I want to perform the stir compare, and what I'm imagining is snacks next name is less than earlier in the comparison than name. So that's what I need to do for my comparison. And so this is gonna, right, so this while loop will enter so long as the next field exists. The name that you find there is earlier in the comparison. Well, what that means for me is that I would like to then progress snacks, right? I would like snacks to then progress to snacks next. And what we have down here is that either one of two things has happened, right? Either snacks next is null or name comes earlier than snacks next name. Meaning that I would like snacks to point to name, or maybe let me state that instead. Stacks points to new because new has this new name. So snacks points to new and new points to whatever snacks next is. Notice that that is true no matter which of these two conditions caused the break, right? If snacks next was null, I still want new to point to snacks next because there's nothing after that in the list, and so it should still point to new. But if um, but if it exists and name comes before snacks next name, then still I want snacks, the current node, to point to new and new to point to snacks next, right? That's this sort of like jog around that I was trying to kind of demonstrate here, where this would be like snacks, this would be like new, and this would be snacks next. And so I want snacks to point to new and new to point to snacks next. So that's what I'm going to do. So no matter what, but I will need a temp variable, right? Because I'm kind of like moving things around, and often when you need to move things around so that you don't lose something in all of the reassignments, you want to make a temp variable. So let's say struct snack star temp equals, and so I think I'm going to make that snacks next. Then I want to redirect snacks next to new, and then I would like to redirect new next to temp. And then at the very end, because I think I'm basically done with almost all of the logic, I just need to return the head. And I think this is it. So I think that's a fairly satisfying, nice implementation. I hope it's right. We'll see in a minute. But anyway, there it is. I think that's what I want to do for the insertion. Okay, let's get to the clear. Now for the clear, I would like to, you might think, okay, well, all I do is I call free on snacks. That's it, right? Why is this even a function? Well, it's a function because that's not all you do. Snacks has a pointer to another node, and that is occupying space that you want to free up. And it also points to another node, and that is occupying space, right, in principle. So we need to free up every single node throughout the linked list. So let's, right, in order to help us to progress, we're gonna, because we're gonna be like cutting, right, we're gonna be freeing things up. And so when you free it, then you're no longer, right, because you freed it, you can't trust that you can follow its next pointer. So you need something to remember what the next pointer was. So anyway, so let's say that I have a temp variable that will just help me to remember things even after some things have been freed. That's supposed to be a struct. In fact, I might as well initialize that to snacks. And then what I can do is say that so long as snacks exists, so I could just simply say that, right, while snacks. This will run when snacks exists, is not null, and it will halt when snacks becomes null. So what do I want to do? I want to go ahead and update temp. Well, actually, temp is already updated, so maybe I updated at the end. So anyway, let's try free snacks, then set snacks, the variable, up to the current value of temp. Maybe honestly what I really want to do is I just want to do an initial check to see whether or not snacks has any next pointer. And then again, by a similar kind of logic as before, always check the next pointer. So let's just say, if not snacks, and in fact, since I would like this check to go at the very top. So if not snacks, then return. But snacks exists now. Since snacks exists, I would like to get its next pointer, but I don't know if it exists. So if not snacks next, then do two things, free snacks and return. But otherwise, snacks and snacks next both exist. And so long as they both exist, then I want a temp variable. So struct snack star temp while temp, right? So long as there is something to progress to, I think that's, I may change my mind. But so what I want to do, because I know that, right, like if you imagine, right, so I know that snack exists, I know temp, the next exists, and I maybe want to assign it actually here. And so long as those things exist, then what I want to do is free up snacks, reassign snacks to temp, update temp. Yeah, I think that's exactly what I want to do. So, okay, so free snacks, snacks, the variable is now temp, temp is now snacks next. And that will go and go until temp is, so that should go and go and go until temp is null. When temp is null, then snacks has still not been nulled. So we want to free snacks still at the last run of this, and maybe now null all of the pointers involved. So, snacks equals null, temp equals null. And I think, is that it? That looks like it. I think that's it. Okay, cool. Right, and I don't do any freeing up here. I simply create things up there. I free things here. I think that's the end of that. Okay. It would be nice to go ahead and test this thing out. That's a lot of writing code without a lot of testing, which sometimes is a little necessary, but okay, let's hope this worked out. Right, so I want to prompt the user for their inputs. The first thing they're going to input is a number of snacks. And so that's an integer, and I want to get an integer variable waiting to receive that information. So int when, which is the number of snacks, and then prompt the user, then grab info from the user, scanf %d address len. Now that I know how many snacks there are going to be, and I guess we could defensively say, if len is actually maybe less than 1, then just don't do anything bad input kind of, but whatever. I'll just do that. Okay. But otherwise, then we've got a positive integer, and we are going to add that many snacks. So I want to do a for loop, prompting for this many snacks. So for int I equals 0, I less than len, I plus plus, printf, enter a name, and scanf string. Oh, right, and I need to initialize the things that will receive this information. So char star, let's say name, and let's malloc space for, I think that would be size of char times 32, because the static array also was declared for size 32. And again, right, like whenever you use scanf with malloc and so on, you really ought to do something defensively to make sure that the user does not input into the string more than the memory allocated for it. Again, that's an important thing when you're taking things seriously, but I'm not taking this that seriously. So, okay, so then there was cost, which was a float, and there was quantity, which was an int. And I think this is all I need to grab from the user. So here I can grab the name, printf, enter a cost, I guess. So that's a float. That's going to go at the address of cost. Oops. Okay, so I've grabbed all the info from the user. Oops, forgot a semicolon. So what do I want from here? Right, I want to or make a call to insert. And and I probably need to keep track of the linked list. So I probably also need to have a struct snack pointer. I'm going to call it LST, and that is initially null, right? Because it's a pointer. Pointer being initially null is the initial signal that this is an empty list, right? It was designed so that we would pass in null the first go around. And we need to always make LST the head of the list, which we can do by saying that LST equals insert sorted LST name cost. Okay, I think that makes sense. And now we just need to print the result of what was entered. So let's say for int I equals 0, I less than len, I plus plus, printf, percent D for the first, like the index of the thing, percent S for the name of the thing, tab, I think it goes cost, tab, quantity, oh, right, and cost I need to say it gets filled with a float, in fact, maybe a 2-digit or 2 decimal place float, and a digit or decimal, and a line break. And that's all going to come from, just for readability, let's put it down here and say that that's going to be I for the first thing, LST arrow name, LST arrow cost, LST arrow quant. And then every time we do this, we progress LST. It returns, so I should return 0 at the end. Before I do that, I should free anything I malloced, and I know I malloced LST, just in case we always null the pointer. I don't think I malloced anything. Oh. But no, we do not want to call free. The whole point of clear was that simply calling free does not do an adequate job on a linked list like that, so we need to call clear and then null the pointer. Okay, I think that might be it. So let's test it out. Let's come down here and say make snack bar, or what is that? Sorted snack bar, run, enter number of snacks. Let's start with just one. A1, 2. Exactly the right behavior. I think, yeah. What next? Try it again, but this time give it 2 things. So 2 snacks. A1, 2, B3, 4. Looks very good. Try one more time. Enter a number of snacks 3. Let's do it not in sorted order. So let's start with B1, 2, A3, 4. C. Where do I want to put this thing? We probably want to test it in all kinds of ways. Tell you what, I'm a little lazy and I'm only going to test this on one more thing because I'm bored and would like to move on. Should I be that lazy? It's ABC. Looks pretty good. It would take B, insert A before it. It would take C, insert that at the end. I guess I've still never yeah, maybe, I guess I gotta do something more interesting. So let's do one more. Just with the feeling that if you didn't, you're really not testing every possible case. Okay, so there's A. I would like to put a B and a D and then call insert, or let's just do, because I am so lazy, C and then I'll put B. So C, 3, 4, B, 1, 1, and it looks right. Okay, cool. So I am not going to do any more. It looks like we got the right thing. The end.